Okay. So today our lecture title will be a process management. So you have learned before memory, conventional one, a virtual memory, and then you also have learned about processor management. Processor management. So now to the next topic, lecture number 5, process management. Okay. There's some analogy for the process management. Okay. Take an example, the staircase. Wait, why is it? For some reason it doesn't. Never mind. Okay, the staircase at the building was built as a fire escape route, but people in the building often take the stairs instead of the slow lift. So it depends whether some of the lift, some of the lift or elevator in the building is very slow, or some is very small. So people tends to go to the stairs. Okay, every building must have stairs. Every building, like in Malaysia, you have like if more than 4 levels, it is compulsory to have a lift, and of course stairs for like fire emergency. So the stairs is only wide enough for one person. Okay, the stairs only wide enough for one person. So imagine this a very small stairs that at one time only one person that can go, or can pass through that stairs. Let's say in normal circumstances, traffic flows is very smooth. Okay, you can go both. I mean, if one person goes, imagine this only one way, depending on the which ways you want to go, either going up or going down. So traffic flows smoothly unless there are two people moving in the opposite directions. So there's a landing between each floor that is wide enough for people to share. Okay, a problem occurs. So you have like a stairs here, and then you have wait, just make a little bit more. So this stairs like really only one person. So, but at the same time, at the each level landing, we call it a landing level, is enough for two persons to like land or stand at one time. But the stair itself is a very small stairs. Only one person, where either he can go up, or he can go down, or he can goes up. All right. A problem occurs when someone going up the stairs meets someone coming down, and each refuse to retreat. So you have here this person wants to going up, wants to going down, and this persons want to go up. So you have here this a deadlock. No one wants to give up, or no one want to retreat to the landing position, either on the upper side or on the lower side. So this situation we call it a dreadlock. You of course you have been in a deadlock situation a couple of times. Okay, so another possibility, a few patient people wait on the landing for a break in the opposing traffic, and the break never comes. So let's say you are in the opposing traffic. We have example diagram for that. And if like nothing happens, no one can go out, or no one can go out. Everyone stops unless there is an outside intervention. This condition will never gonna be solved. So this is what we call a starvation. This is what we call a starvation. So this intro. That is a visualization of the deadlock. So a deadlock in systematic means a situation where the resources needed by a job to finish execution are held by another job. Okay, they just like the example of the stairs. Both of the persons both of the persons or need to do some things. One person maybe have to go to other departments that located down at at the lower level floor, and that another person have to go to the department that on the upper level floor. So the resources is the stairs. So needed by job to finish again are held by another job. So this is a deadlock situation. The resources are needed by both men, but at one time only one person can go up or go down, goes up or goes down using the stairs, which in turn is waiting for other resources to become available. No one wants to give up. I don't want to give up. I will just wait here. If I just wait here until at the end of the time, okay? I don't want to give up my position here. So also it is also sometimes termed as a deadly embrace. Okay, deadly embrace. So these are deadlock situations. Okay, a sticky situations. And then you have a starvation, the results of conservative allocation of resources in which job is prevented from executing because it is kept waiting for resources that never become available. So this like the keyword, the conservative allocation of resources in which a job is prevented from executing because it is kept waiting for resources that never become available. So you're waiting in the traffic jam, but it's like really bad traffic jam. No one can move. So this is a diagram of we don't have a diagram yet. So imagine it's a traffic jam, which I think slide number 6 or something. So deadlock affects more than one job. Okay, imagine that person that doing going up or going down using the staircase. Okay, it affects more than one job. That person is a job. Example of deadlock: traffic jam. Only outside intervention can resolve a deadlock. Okay, unless there if there is no outside intervention, it's gonna be there forever, starvation. Unless of course in OS you can just forcibly shut down the PC or control alternate delete or something. Okay, and you end tasks and the jobs, whatever job you just feel annoying or taking too much processors load. Deadlocks are prevalent in interactive systems like the modern time because the system is more flexible than a batch environment. Batch environment where, just to recall, where the jobs is coming in batch, in a groups. You settle that batch first, and then another batch coming in. The interactive system is a dynamic, more dynamic, it's based on demand. Okay, it doesn't like save or allocate any memory, allocate any resources. If allocate any idle resources, this is what we call interactive systems. And interactive system improve the use of resources through dynamic sharing, but this also increase the possibility of deadlocks. Okay, this is the where the traffic jam, a deadlock in the traffic jam. Okay, where okay, this, let's say this and this one as well cannot move on this side, on this side. So okay, on this side. So any of the direction the car cannot move because this is a deadlock. Okay, unless like some intervention or something, meaning that the police traffic only allow a certain route to be to clear first, or maybe some accidents happens if still waiting for the police or the ambulance to take the or tow truck to take the uh, affected vehicles or to take the patients. We are stuck in the deadlock or sticky situation here. So no one can move forward until someone moves out of the way. No one can move out of the way. Okay, you cannot continue because someone have to move forward, move out of the way. But there are no one that can move out of the way until someone advance or real line moves back. So only as I mentioned, only outside intervention can solve these issues. So it usually occurs when the non-shareable preemptible resources, files, printer, so in the OS, in the computer systems, are allocated to jobs that eventually require other non-shareable, non-preemptive resources that have been locked by other jobs. You have to wait. Files, I mean printers and everything have to wait until that job's to be done. So you have here 6 cases of deadlocks. First, the deadlocks on the file request. And then deadlocks in the database management, dedicated device allocation, deadlocks in multiple device allocation, deadlocks in spooling, or deadlocks in hard disk sharing. So first we go into the deadlock on file request. It happens when jobs are allowed to request and hold files for the duration of the executions. Wait, sorry. Okay. So jobs are allowed to request and hold files for the duration of the execution. Example, a home construction company has 2 departments, a purchasing P1 and sales P2. Both departments need access to 2 files, which is inventory F1 and the suppliers F2. Yeah, for some reason I cannot use my tab. Never mind. Okay, a home construction company has 2 departments, purchasing P1 and sales P2. Okay, and then they have to access 2 files on the PC, inventory F1 and suppliers F2 to update the daily transaction. So a deadlock occurs when the following sequences of events takes place. Purchasing P1 accesses the supplier file, F2 to place an order for more lumber. Okay, deadlock occurs when the following sequence of events takes place. So purchasing P1 access the supplier file. So you have a like a file. I mean you have a purchasing P1 here, and then access the supplier file F2. Sales P2 access the inventory file F1. So sales P2 F1. So first they try to request. I mean the P1 request, and it is F2 allocated space for P1. This one is allocated. And then you have a sales P2 access the inventory file here. Try to access the inventory file, it requests. And F1 allocated the resources to P2. P1 doesn't really, okay, sales P2 SMF to reserve parts that will be required to build the house ordered that day. So at the moment, P1 doesn't release F2 because P1 is using F2. But at the same time, he needs, P1 has to access the inventory file for some other matters. So he tried to request the F1 request. F1 to verify the quantity on hand before placing an order, but P1 is blocked. So when F1 heard the request from P1, but it cannot allocate the resource, to FP1 because at the moment is serving P2, process 2 or jobs number 2. So this is the jobs, this is resources. F1 is the resources. So it blocked here. And P2 doesn't release F1. Okay, P2 doesn't but request for F2. At the same time, P2 also want to request F2. Okay, he wants to check something. But F2 at the moment allocates its resources to F2. So this one will be blocked. P2 doesn't release F1 but request for F2 to check. So this is a deadlock situation. So this you have your request. Okay, this is the first one. Purchasing P1 need to purchasing P1's need to request suppliers F2, and it is allocated. So number three, inventory F1 requested the sales P2, and it is sales inventory will be allocated to F1. Sorry, this is the really wrong one. So this is allocated. And then at the same time, number five, P1 try to access the inventory. Okay, try to access the inventory F1, but the request is blocked because at the moment F1 is serving P2, and P2 try to access the supplier F2, try to request, but it's blocked here. Both here block because at the moment supplier F2 is serving purchasing P1. Okay, so you get I hope that you get the idea of the deadlock on the file request. Then we have a deadlock in the database. So we have a deadlock in the database. So occur if two process access and log records in database. Okay, you have a two database. Somehow you have a database. You have a multiple database files. Like okay, this is database for the list of customer, and this is database for the list of suppliers. List of mean a multiple databases file. So one of the way to manage the deadlock in database is by locking. Sorry, is by using locking. Locking is a technique used to guarantee data integrity by locking out other users while working with the database. So data integrity, meaning that locking is used to protect or to guarantee the data integrity, meaning that any files or data is not modified. Okay, it's not modified or being altered. So this is what we call integrity. The files is as it is, not modified or not altered. Data integrity. So you lock that part of the file. So you lock, okay, where while you serving other users, you lock other users to access that database file. Okay, let's say this user one is DB1 database one is now DB1 is allocated to user 1, but user 2, user 3, user 4 try to access DB database 1, but they are all blocked because it is now allocated locking. User 1 already locked database 1 for him to access the resources and the resources to serve him. Locking can be done at three levels. Lock the entire DB for duration of the request. Okay, until user 1 finish everything, it will release back, lock a subsection of the DB. Maybe DB you have a couple of, okay, a name, metric numbers, name, metric numbers, grade. What else you have? I mean, you have a different column. So you lock one column, you only lock one column, while the other two columns anyone can access that. But the column that has been locked, no one can alter that, maybe view or something. Or lock individual record, just a number of individual. Let's say John here, you have John Smith, Ali, Ah Chong, and you only lock John. This like John here, John, you only lock that part, the individual file, lock the individual record. So locking increases the possibility of deadlocks. So because you lock, So anyone, only that part. It's like a toilet, okay? It's like a toilet that only have one if you going number two. Only have one, so it's a deadlock situation. No one can use that toilet unless that current user finish. Of course. And of course, if you not, flush, if it does not flush or whatsoever, or the stop, everything, pipe stop or something, or no waters, you still cannot use. So this imagine is like a toilet that have only one toilet bowl. All right, before you going number two. So another example is a system logs a record when it's accessed until a process is complete. Two processes P1 and P2 need to update two records, R1 and R2. So the following sequence lead to a deadlock. P1 access R1. So this one P1 and this one is R1. P1 what? Two processes and two records. So P1 and and R1. So P1 request and allocated. Request and allocated. And then you have a P2 here. And you have here R2. You want to access the record, so you request, and this one you allocated. Sorry, request should be a dot line. Dot line. Just bear with my handwriting. Okay, request, and this one is allocated. P1 request R2. So now P1 wants to request R2. I am greedy. I need R2 as well. Sorry, this is supposed to be a. It's supposed to be a when I just want to you know try to separate between the request and allocated. So request R2 request. But P2 already locked record 2. No one can use R2 except for me. So it is blocked here. And at the same time P2 try to request R1. Try to request R1 request. But it's also blocked because R1 is serving or being allocated to P1. So if you do a too many locking, to call that too conventional, okay? You don't want someone else to access it except you. While you entering this or while you're doing that, no one can disturb you. So you will increase the deadlock situation. People might hate you, okay? So alternatively, do not use locks, but this may lead to integrity problem, okay? Data can be easily modified in a wrong way or data can be altered, okay? Many bad guys love this. The updated record also might include only some of the data, okay? Some of the effect of you don't do the locking. Some of the updated records might not include a sum of the data. It's not correct. So this is known as a race condition. Let me show you. Like, okay, you have let's say you have a one process that you have a one process here. Read x, okay, and then write x equal to x. So W is write, this one read x, and W you write x equal to x plus 10. So the program read x first, so x a shared date, x is a 10. So read x and put x equal to 10. And then write x plus 10, so x is equal to 10 plus 10 is 20. So the final value being recorded is 20. But let's say you have a where's the place? Let's say you have a two process. This one read x. Okay, x a shared variable. Okay, x a shared variable. X is a shared. variables. So read x and write and write x equal to x plus 10. And of course you have, this is the process 1, and you have a process 2. Also read x and write x equal to x plus 10 as well. You have that. You have two process. Okay, the first process, let's say, come at not at the same time, but almost at the same time. So first you have process 1, read x. So it's recorded x is equal to 10. This one first, okay, this one number 1, and then suddenly P2, also this process that this is the like thread process that been chopped into smaller threads. So number 2, process 2 read x. So process 2 also we record x is equal to 10. Let's say come back to this one, thread number 2. So this is number 3. So x will write, the process will write x is equal to x plus 10. So process 1 will record here x is equal to 20, 10 plus 10. But this is a process, this is thread number 4 comes in. So process number 2, thread number 4 still read x equal to 10. And when it wants to write x plus 10, it will write x 10 plus 10 also 20, which is wrong because it's supposed to be 20. This, in order for you to prevent this, you must log, meaning that you done the P1 first. So when you done a P1, x will become 20, and when the process number 2 try to read what's the current value of x, it will read 20, and 20 plus 10 is 30. So this is what locking try to prevent, a race condition where you suffer data integrity. Data has been modified or altered in a incorrect way, in a wrong way. But of course, if you lock too much, your system will be too slow, and it's not dynamic. Okay, this is a parallel programming problem, so we will not cover. But I'm showing you the race condition, the simple one, the read and write x. So this is examples from the slides. So Chow, you have a GPA of 2.5, and currently he stays in College 12 or 12 residential college. Okay, 12 residential college. Any one of you stay in a 12 residential college?
No.
I think
Nope.
science computer mostly 8 and 10. I think so, but 12 residential college. I have become a fellow there before. It's the biggest college at the moment in UM, and because it's the biggest, newest, he has a very, he has a very nice floor, and it has his it has a very nice room, and it has his own lake or some lakes, even outdoor gym. Okay, I have been a college 12 before, a fellow. Now I'm fellow of second college. So you have Chow GPA 2.5 and address college 12. All right. Okay, process 1 only grade process, reads data. Okay, reads data, grade process and reads data. Grade process meaning that write a new value to the process. Reads data, reads grade process. Sorry, this is a grade, only modify grade. Okay, grade GPA, and it reads data, only reads data, doesn't do anything to data. And process 2 only address process, address, the address part, and only reads the, okay, reads the data. Sorry, reads the data as well. So Chow actually got a GPA 3.0 in the new semester. In the current in the previous semester, the semester that just recently finished. Okay, but GPA updated, grade process. So it doesn't like modify. It still thinks the process one still thinks Chow is in the 12 residential college. But process number two only address process update. I mean updated the address. Updated the address, only read the GPA. So actually, Chow already moved out from 12 residential college to section 17. Okay, section 17 PJ. Maybe Chow is not really active, so he has been kicked out from the college. Okay, if you want to stay in the college, you have to be active in the student activities, sports or arts or whatever activities, and of course you have to like attend the programs that managed by the colleges. So if you don't attend that, you got demerit and stuff. So child don't have enough marks to stay in the college, so he has to move out. So this one child only address is updated but not the GPA. So the first process one rewrites record to the database file with a new GPA, but it reads GPA 3.0 and address code is 12. It does not update the new location where Chow transferred to. But when and then P2 update the database file, P2 rewrites record to DB. Rewrites rewrites record to DB. It only update address but not the GPA. Okay. The system said, okay, Chow, you are not attending last semester. So your GPA is 2.5, or you failed the whole subject, your GPA is still 2.5, something like that. But we have a record of you moving out. So this is wrong way. This is the what we call a race condition. Process 1 and process 2 try to process 1 and process 2 try to what we call that, try to compete to each other, try to compete with each other to update the record. So this one. So it also can be a reverse situation where P2 comes first and then P1 rewrites, but still it will return the same problem. If like P1 rewrites, P1 only have this one. GPA is correct, but address is 12 college. 12 college, which is wrong. Still a race condition problem. Okay, now we go to the deadlocks in, I think this is number 3, yes. Deadlock in dedicated device allocation. Two users run two programs, P1 and P2. And both programs need two tape drives to copy file from one tape to another. Just imagine your hard drive. Maybe one to you from your thumb drive to your SSD or something else. So the following sequence leads to the deadlocks. P1 requests tape drive 1 and gets it. So P1 tape 1. P1 request and allocated. P2 requests tape drive 2 and gets it. So P2 tape 2. Request allocated. By the way, this visualization of a direct a visualization of okay, there is one in mathematics. There is one field that is called graph theory. Graph theory. Okay, this one represent nodes. Okay, this whatever this represent P1, T1, P2, P2 represent nodes, and this one is a direction. It can be both way, like it can be bidirectional or one directional. Bidirectional or directional. Bidirectional means two ways. Directional only one way. Okay, this is what we call a graph theory. Just for you to visualize. We use a lot of graph theory in the science computer. Okay, we use a lot of graph theory in science computer, regardless what courses you are. Not even not just science computer, used in medical, engineering and others. Okay, now we go back. P1 request tape 2 drive by this block. Same. P1 tries to request maybe some files are allocated in T2 request, but it's blocked. It is blocked here. And P2 try to request T1, but it's also blocked because of course T1 is allocated or serving P1 and T2 is allocated and serving P2. Neither job can continue because each is waiting for other to finish. No one wants to back down. Okay, you have to force it to stop the operation. You have to force one of the process to stop the operation, terminate. Or if you just if like become the situation become too difficult to control, just restart the PC. Okay, that is the simplest troubleshooting that you can do. Of course it's easy, but you don't it's not really effective, but it works. Believe me, it works every time you try. If you don't have any ideas, just plain lazy to to investigate what's the problem, you just restart. This is a basic troubleshooting for all electronics problems. So dialogues occurs when several processes in multiple device allocation. Occurs when several processes request and hold on to dedicated devices while other processes act similarly. Okay, so there you have a several process request and hold on to dedicated devices. None of the jobs can continue because each is waiting for resource help. But just similar with others deadlocks, deadlock situation. So you have here, okay, P1 try to tape drive allocated, and then where's okay? This one is number one, number two. Printer, request P2 request a printer and is allocated. Now P2 is using the printer. Okay, good. Five is what? P3 try to request the plotter. The plotter, I'm not sure. I mean, never mind. A plotter and try to allocate. I mean, request and successfully allocated to P3. 5 and 6, okay, so far so good. I mean in order the request tape drive, printer and plotter is okay, but now where's number 7? Now P1 already access the tape drive. Okay, I need to print this, so request to the printer, but at the moment P2 have his final year report of his thesis, very thick thesis, wants to submit at last minute. So now I'm using the printer, no one can use it, it's a shared printer. So P1 has P1 requested, so it is blocked here. So this one is not okay. Where is number 8? Oh, 8. So now P2, oh, I need something. I need to, okay, before I can print to the next page, I need to use plotter. I'm not sure why he need to use plotter. He tried to request the plotter by this block. Okay, block. So this one is not okay. So P2 cannot continue print because at the maybe some of the pages he needs plotter. I'm not sure what he needs plotter for, but he has to hold for a while or wait the printer to finish. But at the same time, P1 want to use printer. He has to wait P2 to finish using printer. So it's block 8, where's 9. So at the moment P3, oh, I think this file is on the tape drive. So request the tape drive, but it's block request. It is blocked because tape drive is allocated to P1. So you have all this sticky situation. No one can finish their jobs because it's blocked. Okay, no one want to back down. Of course, you can shut down PC2, everything. You have to start over, and P1 can access the printer and stuff. All right, only you shut down one. Call control alternate delete and task, something like that. But it's not effective way. Again, this very lazy plain way. And then you have a deadlock in spooling. Although a printer is a dedicated device, it can be transferred. Dedicated mean when you do, okay, you send you control P, you want to print something from the slide, so it is a dedicated device at that time, dedicated to serve you. It can be transformed into a shareable device by installing a disk between it and CPU. Of course, you can, I mean, in Windows, in Linux, you can You just can configure it to be shared devices. The disk accepts output from several users, okay? Several users, and act as a temporary storage area for all output. Act as a temporary storage area for all output. The disk, mean if all users, you have user one, user two, user three, try to do, doing some assignments last minute. Typical student last minute, they need to submit. So everyone rushing to print something to submit to the lecturer. So until the printer is ready to accept it, this is known as a spooling. Okay, temporary storage. Until printer is ready to accept, this is known as spooling. Your manager, your task manager. If the printer needs all of jobs output before it begins printing, but the spooling system fails the available disk with only partial complete output, a deadlock occurs. Okay. So in order for you to print, let's say this assignment needs you to print 10 pages. So but it receive like 1 pages first, 2 pages, 3 pages. At the same time, user 2, okay, user 1, this is a shared printer, okay, user 1, what happens here, right, okay, this one is a user 1, user 2, and user 3, okay, user 1 send, but pages by pages, you have, okay, user 1, maybe 10 page, 10 page, and 10 page, user 1 send, but maybe the printers only receive like page 1 until page 4. U2 maybe page 1 until page 8, and U3 maybe page 1 until page 7. Your printer needs all job output before it begins printing, but the spooling system fills the available disk space with only partially completed output. The deadlock occurs. Okay, user 1 cannot print because only 4 pages submit to the shared printers. User 2 also only until page 8, and user 3 until page 7. So this is the deadlock situations. Okay, everyone rushing want to use only one printer. Okay, the deadline for assignment completion is like 1 hour from now, but no one can print to submit. Of course, you can submit online. This is just example. So, okay, 1 hour before important project deadline, members of your teams are frantically finishing the details. So, a last minute submission. A few minutes before deadline, all team members issue the print command. Everything all comes together simultaneously. The spooler receives the pages one at a time, but the pages are received separately. Page 1, page 2, and so on. So the printer is ready to print the first completed document. In order for the printer to print, it must be a complete document. If 10 pages, 10 pages. No compromise. Okay? No compromise. I need 10 pages. If not, you cannot continue this job. But as the spooler canvasses its file, it has the first page for several documents, but none of the complete document. As I said before, user 1 maybe have 4 pages, user 2 only have 1 to 8 pages, and user 3 1 to 7 pages. Since the printer only accepts completed files, the keyword here, completed files, none of the documents can be printed, and you cannot submit your assignments. Right? So this deadlocks in spooling. Deadlocks in this sharing, okay, all of the deadlocks have a same, have a same, what you call it, same process, same SOP. We call it SOP, famous word now. Everything SOP. So these are designed to be shared. These are designed to be shared, not uncommon for two processes to access different areas of a disk. So you have like a solid state device, you have a sector. I think you will learn this in a computer architecture where it is allocated into the several sector of the disk. Sector, several location. Sector is a location in your disk drive. This ability to share creates an active type of deadlock term, live lock. Yes, who's that? Okay, guys, finish. All right. Process use a form of busy waiting that is different from natural wait. It's waiting to share resource but never gains control of it. Okay. They are so if you are able to share creates an active type of deadlock terms live lock. It's just similar with the locking. Processes use a form of busy waiting that is different from natural wait. It is waiting to share resource but never gains control of it. Okay. We have here. So you have a customer service here, P1. P1 wishes to show a payment. Okay. Wishes to show a payment, so issues a command to read the balance, which is stored on track 20. Track 20, a sector on track 20. Okay. Sector in 20. Okay. Sorry, pen here. Okay. Sector in track 20. Uh, while the disk control unit is moving the arm cylinder to 20, P2 is put on hold on the input output channel. Okay. Yeah, sorry, P1 is put on hold on the input output channel. Put on hold on the input output channel to free the process of the next input output request. Okay, P1 is and P2 gains control of the input output channel. So now P2 gains control of the input output channel and issues a command to write another record that is stored in cylinder 3110. So we have a cylinder 3110. So P1 now is a P2. Want to access the location of 3110, 310, sorry. And then if the command is not logged out, P2 will be put on hold while the control unit moves to the arm cylinder 3110. So because like P2 is on hold, the channel is free to be captured again by P1, which confirms its command to read from cylinder 20. So since the last command from P2 had forced the arm machines to cylinder 310, the disk control unit is beginning to reposition the arm to cylinder 20 to satisfy P1. The input output request channel will be released because P1 is once again put on hold. Alright, P1 is again put on hold. So it could be captured by P2, which is a write command only to discover that the arm mechanism need to be repositioned. As a result, arm is constantly moved back and down. So it's like a deadlock. It's like a deadlock situations. The arms move 23, 310. Move here and then keep on hold, then move here back. 20, 110. So it goes into the loop. Alright, this is the condition for deadlock in this sharing. So all 6 deadlocks involve the interaction of several processes and resources. Each deadlock is preceded by the simultaneous occurrence of 4 conditions that the OS could recognize. Okay, it's preceded by the simultaneous occurrence of 4 conditions that the OS could recognize. First is mutual exclusion, meaning that you allocate a critical section. Okay, critical section, meaning that let's say you have a long list of the commands, long list in your coding, long list of coding, but there are some critical section, meaning that if the jobs are currently on this section, it must be completed first before you can move out to other section, other command. So this is mutual exclusion. Resource holding. So you want to avoid avoidance of deadlock, you must release the resource holding. You hold the resource. Only me can use these resources. Only I can use these resources. No one else. No preemption, meaning that you don't like allocate specifically for these jobs, and you have a circular way or in a round robin fashion.